In the early 1800s, electricity meant sudden jolts, crackling sparks, and batteries that seemed almost like chemical tricks. It felt useful, but not predictable. Researchers charged objects, watched tiny bits of material jump, and timed how quickly a spark leapt across a gap. They recorded effects carefully, but each setup looked like its own little world. The big question stayed unanswered. What exactly was electricity? Magnetism sat in a different box. A compass needle turned, iron clung to lodestones, and magnets pulled or pushed in ways that looked steady and stubborn. People mapped where a compass pointed and how force seemed to fade with distance, but it stayed a separate craft from electrical shocks and sparks. There was no shared language for them. If electricity acted like a sudden event, magnetism acted like a constant presence. Light, meanwhile, belonged to yet another story. It got studied through lenses, mirrors, and prisms, with arguments about rays, waves, and colours. It could be bent, split, and focused, but it did not look like a force that grabbed metal or made sparks. So 3 subjects grew side by side, each with its own tools and rules. No single set of numbers tied them together. They did not yet look like parts of one system. In 1820, a Danish scientist named Hans Christian Ørsted made a simple test that carried a shocking consequence. He sent an electric current through a wire. Nearby, a compass needle did not stay pointed north. It shifted. The current had done something to the magnet without touching it. Until that moment, electricity and magnetism had looked like separate tricks of nature. Now one effect appeared to create the other. That tiny swing of a needle changed the rules. It meant a current did not just heat a wire or make sparks. It also produced a magnetic influence around it, strong enough to push on a compass from a distance. Magnetism was not only something found in lodestones or iron. It could be made on demand by moving electric charge. A link had been demonstrated in plain physical behavior. Once that link existed, it raised a new kind of question. What exactly surrounded the wire that made the compass turn, and how far did it reach? The observation did not yet give an equation, but it forced a shift in thinking. Electricity could create magnetism. That was the first bridge. And with a bridge, the next step became unavoidable, finding out whether the traffic went both ways. Ørsted's result already felt like a one-way bridge. Electric current, then magnetism. But it left a sharp question behind. If electricity could make magnetism, could magnetism make electricity? For years, that idea sounded like a wish more than a fact. Then, Michael Faraday approached it with a simple rule of testing. Push the magnetism, watch the electricity. He searched for a situation where magnetism did not sit still. Faraday found it in change. A magnet held steady near a wire did almost nothing. But when the magnet moved, or when the magnetic strength shifted, the wire suddenly produced a brief electric current. The effect appeared only while something changed. Stop the motion, and the current stopped. Start it again, and it returned. Magnetism had not acted like a static pull anymore. It had behaved like a trigger. That single pattern rewired the relationship. Electricity had produced magnetism, and now changing magnetism had produced electricity. Cause ran both ways, but not symmetrically. It depended on motion, on timing, on how fast the situation shifted. That detail mattered because it hinted at a hidden machinery underneath. This could not be explained as 2 separate tricks. It demanded a deeper picture that treated electricity and magnetism as parts of one process. The new link between electricity and magnetism raised a problem. Old physics treated forces as if they reached across empty space instantly, like invisible strings. That picture started to fail. Researchers needed a way to describe what happened everywhere between the source and the effect. A German mathematician, Carl Friedrich Gauss, helped reshape the language. He expressed electric and magnetic influence as something spread through space, measurable in every region, not just at the endpoints. Gauss's key move sounded simple, but changed everything. He connected what happened inside a volume of space to what crossed its boundary. His equations tracked flux, the amount of electric or magnetic influence passing through an imaginary surface. Suddenly, charges did not just pull at a distance, they filled the surrounding space with a pattern that could be counted. Even more striking, magnetism behaved differently. No matter how the surface got drawn, there was no net magnetic flux pointing outward, as if isolated magnetic charges never existed. Michael Faraday pushed that spatial idea further without relying on heavy math. He described lines of force that curved from place to place, showing how electric and magnetic effects occupied space as real structure. When conditions changed, those lines shifted and pushed on nearby charges and currents. The action no longer looked instantaneous, it looked dynamic. Cores travelled through space as a changing field. That new picture did not yet unify everything, but it built the stage where one set of equations could. By the mid-1800s, the pieces existed, but they did not yet lock together. Then, James Clerk Maxwell took the scattered rules of electricity and magnetism and wrote them in one tight mathematical set. It was not just a tidy summary. It was a single framework where electric fields and magnetic fields had to cooperate, moment by moment, in space. Separate effects now shared one language. One system replaced a patchwork. But the new system hit a problem when it followed currents. In ordinary wires, a moving electric charge made magnetism, and the equations behaved. Yet in a charging capacitor, the current seemed to stop at a gap, even though the electric field across that gap clearly changed. The old equation treated that as a break in the story. It made magnetism appear and disappear depending on where you looked. That could not stand. Maxwell fixed it with one bold addition. He treated a changing electric field as its own kind of current. He called it the displacement current, and it restored continuity where the old picture snapped. Now, magnetism responded not only to charges flowing through metal, but also to electric fields building and fading in open space. The equations became self-consistent. Electricity and magnetism no longer merely interacted, they formed one connected machine. Maxwell's equations did more than tidy up electricity and magnetism. When Maxwell treated them as one system and followed the math where it led, something unexpected happened. The equations did not sit still. They insisted that a changing electric field created a changing magnetic field, and that changing magnetic field pushed back again. Once that loop started, it did not stay local. It moved outward through space as a self-sustaining disturbance. That moving disturbance behaved like a wave, even with no wires to carry it. Maxwell could calculate how fast it had to travel using numbers already measured in electricity experiments. The speed came out as a specific value, not a guess. Then the shock landed. That value matched the known speed of light, not close in spirit, close in measurement. The equations treated this wave as an unavoidable consequence of how fields changed. So light stopped being its own isolated mystery. It became the visible part of a bigger story, an electromagnetic wave made of electric and magnetic fields travelling together. That meant optics and electromagnetism belonged to the same framework, whether anyone expected it or not. A lantern, a spark, and a magnet now shared a common description. One set of equations did not just connect forces, it redefined what light was. Maxwell's equations had made a bold promise. Changing electric and magnetic fields should not just sit there. They should travel outward as waves. But for years, it stayed a paper prediction. Then a young German physicist, Heinrich Hertz, took the idea as a challenge. If these waves were real, someone should have been able to make them on purpose, and just as important, someone should have been able to catch them. Hertz used fast electrical sparks to force currents to change abruptly, because Maxwell's theory said sudden change mattered. Near the spark source, he placed a simple detector, a loop of wire with a tiny gap. When the transmitter sparked, the detector sometimes sparked too. No wires connected them. The effect appeared and vanished with distance and orientation, exactly like a wave spreading through space, not a hidden current sneaking through matter. That small secondary spark carried a huge meaning. It showed that electromagnetic waves existed beyond the realm of visible light. At longer wavelengths, the eye could not sense. Light had not been a special, separate thing after all. It had been one slice of a bigger family. With Hertz's evidence, Maxwell's unification stopped being an elegant guess and became a working description of nature, one spectrum, one set of rules, many forms of radiation. Maxwell's equations carried an awkward surprise. They set one fixed speed for electromagnetic waves, no matter what, but Newton's mechanics had treated speeds like simple additions. Move toward a wave and it should have seemed faster. Chase it and it should have seemed slower. That expectation worked for sound and water waves. Light refused to play along. One part of physics said speed depended on motion. The other said it did not. As measurements tightened, the conflict sharpened into a choice. Either Maxwell's unification was only approximately right, or Newton's picture of space and time was. Special relativity resolved it by changing the rules underneath both. It kept the speed of light fixed, but it paid for that with new behavior. Time and distance shifted depending on motion. The older absolute clock and ruler idea quietly failed. Then relativity delivered a deeper twist. Electricity and magnetism stopped looking like two separate forces that happened to cooperate. They acted like two faces of one electromagnetic field, seen from different states of motion. What looked purely electric in one frame could appear partly magnetic in another. Magnetism became electricity viewed through motion and vice versa. Maxwell's equations did not just unify phenomena, they demanded a new structure of reality. By the mid-1900s, electromagnetism already looked like one clean, unified force. But another force quietly ran the universe in a very different way, the weak force. It handled certain kinds of radioactive change, and it seemed to ignore the neat picture that worked for light and electricity. Then a new idea formed. Maybe these were not truly separate forces at all, just different faces of one deeper system. The key step came when physicists built a single framework that placed electromagnetic effects and weak effects side by side, locked into the same mathematical structure. It meant the forces could split apart in everyday conditions, yet still belonged to one combined electroweak force underneath. This was not a loose analogy. The equations demanded specific ingredients to make the union work, even if nobody had seen them yet. Those missing ingredients arrived as a hard test. The theory predicted heavy carrier particles for the weak force, called the W and Z bosons. If the electroweak idea was real, these particles had to exist, with particular properties and masses. Experiments eventually produced them, and the match mattered. It showed that a single set of rules really did tie together forces that once looked incompatible. By today, Maxwell's equations had stopped being a clever idea and started being a working blueprint. They had quietly sat inside the things people used every hour. Power grids had relied on them to move energy across countries. Radios, Wi-Fi, and satellites had depended on the same rules to send information through space. Even medical scanners had used controlled electromagnetic fields to look inside the body. What once seemed like separate tricks had acted like one system. The unification had gone deeper than gadgets. In quantum field theory, the modern language of particles, the electromagnetic field, had still followed Maxwell's structure, but it had been quantized, broken into tiny packets called photons. The equations had not been discarded. They had been absorbed and extended. This mattered because it showed a pattern. When physics advanced, the old unifying rules often survived at the core, reshaped rather than replaced, and yet the bigger dream had stayed unfinished. The Standard Model had tightly organized electromagnetism, the weak force and the strong force, but gravity had resisted being folded in. Gravity had described smooth space and time, while the other forces had lived comfortably in quantum terms. Researchers had chased a single framework that held everything at once, because Chapter 1's disconnected world had looked temporary. Maxwell had proved separation could be an illusion.